Welcome to homework.
So we're asked to determine which of the following relations on the set of functions that are transformations from the integers to the integers are equivalent relations. So in A we have the set f of g such that the function f of 1, the function f at 1 is equal to the function g evaluated at 1. Well, if f of 1 is equal to g of 1, if that's the condition, then it's clearly reflexive, symmetric, and transitive, since everything inside the set is all the same. So A is an equivalence relation. I'm going to call it EQR. And then for B, we have the set. We have the same thing. We have f comma g, where f of 0 is equal to g of 0, or f of 1 is equal to g of 1. Well, we can already see that it's not transitive. So if you have f of 0 equals g of 0, and then you also have g of 1 equals p of 1, then you don't have f of 0 equaling p of 0 and f of 1 equaling p of 1, so it's not transitive. Because there's an or here, so you can have only one of these equalities being true at a time. You can have, yeah. And then for C, we have the set where f of x minus g of x is equal to 1 for all x. So here we have f comma g, where f of x is equal to g of x for all x in z. Well, if f of x is equal to g of x, f of x minus g of x, wait, no, sorry, C says f of x minus g of x is equal to 1 for all x in z. Well, if you have f of x minus f of x, that's equal to 0, and it's not 1, so it's not reflexive. If you take the relation of f of x on f of x, so if you have f comma f, then you get f of x minus f of x, which is obviously equal to 0, and it's not equal to 1, it should be equal to 1. So that implies it's not reflexive. X, f cannot be related to itself. And for part D, we have instead of the set f comma g, And for some C and Z, we're told for some C and Z, so in other words, there exists a C and Z such that for all X and Z, f of X minus G of X is equal to C. This is what we're given. Well, let's check if it's reflexive. If you have f related to f, then you get f of x minus g of x, and that's just equal to 0. So there exists some c and z. 0 is inside the integers, so that works. So it's reflexive. Now let's check if it's symmetric. So if f is related to g, and that implies g is related to f. Okay, so if f of x minus g of x, so then the first one gives us f of x minus g of x equals some c, and then g of x minus f of x gives us another c, and we know both c's are in z, so c and c1 are inside the integers, so that implies it's symmetric. Because the condition is that there exists some c, and we found two c's here, c and c1, that are both inside integers, so that implies it's symmetric. So now let's check if it's transitive. If you have f related to g and g related to, call this p, and that implies f is related to p. So let's see if that's true. If you have f of x minus g of x equals some c, and g of x minus p of x equals another c, and then you have f of x minus p of x is equal to another c, where all three of these c's are inside this z, so all c sub I are inside z. That implies it's transitive, because that was the condition. We just need to have a c that's inside z. Now let's check the last set. They give us set E. In E, we're told we have f comma g such that f of 0 is equal to g of 1, and f of 1 is equal to g of 0. So let's check reflexive. Reflexivity implies that f is related to f, right? So we have, that implies f of 0 is equal to g of 0 equals to f of 1, and f of 1 is equal to g of 1, f of 1. But you can have a function where f of 0 gives you some number, and f of 1 gives you a different number, b. So you can have where f of 0 might not be equal to f of 1, so it's not reflexive. and therefore it's not an equivalence relation. So the only equivalence relations we got were A and B, and the rest were not equivalence relations.